Hello everybody, welcome to my channel, and today we will discuss hybridization. Let's first figure out what hybridization is and why it is so important. As we see in the picture, we have s and p orbitals. When they create bonds, but pay attention, sigma bonds, one s and one p orbitals with different energies, they will hybridize and come to two orbitals which have the same energy, so they will be called hybrid orbitals. Pay attention at this picture. We have imagined that one s orbital, you know that s orbital had the form of sphere, and one p orbital like the dumbbell. When they hybridize, we get two hybrid orbitals, and that will be sp hybridization. What if we have two p orbitals? In this case, we will get three hybridized orbitals. We will have one s and two p orbitals. It will be sp3 hybridization. Sp2 hybridization. 1s and 2p, sp2 hybridization. So overall, three hybrid orbitals. And now let's take examples. For instance, we need to find the hybridization of SO2. In order to find it, we have to draw the Lewis structure. Let's draw a Lewis structure with all electron pairs. And in order to find how many hybrid orbitals we have to count the number of bonding areas, or let's say number of electron areas. Not the number of pairs, not the number of bonds, not the number of electrons, but the areas where there is bonding. For instance, if we have the double bond, it's one area anyway. So we have 1, 2, and 3 areas. You enumerate them. Look, lone pair is also considered as the electron area. It means we have 3 electron areas. 3 means 1 plus 2. We know 1 will always be S, and we have 2 p orbitals here. Why we say that S is always 1? Because we know that S orbital, S subshell consists of one orbital only, so we cannot have more than one orbital on S subshell. It means that we will always have one S orbital. P orbitals can be 1, 2, or 3, because on P subshell there are 3 orbitals. They can be hybridized, all of them, or 2 of them, or just 1 of them. So in our case, we have 1 s and 2 p orbitals, which are hybridized. And it will be sp2 hybridization. Well, as you see, 1, 2, 3, these hybridized orbitals, I will make them green. They show that how many sigma bonds we have. Even lone pair is considered like sigma. The other, we have 2 more p bonds here. We see they are purple. These p bonds are created by non-hybridized electrons. And let's now write it. And if we write its electron configuration, we see that it has 6 valence electrons. 3s2 and 3p4. We know that s orbital has lower energy than p orbital. Let's draw them. There are 3s, and here we have 3p. In the diagram with energy, we draw it in this way, s and p. Let's draw 3s2. We draw 2 s electrons. And on 3p, we have 4 electrons. Let's draw them. 1, 2, 3, 4. Indeed, we know that this is our ground state. If our sulfur atom gets excited, 1 electron from 3p will go to the empty 3d orbital. 3d orbital, yes, like one of the orbitals on the 3d subshell, because we know that sulfur is on the third pair. In the third period, it has an empty d subshell, so 1 electron will move there. Well, if we draw it, we can see one of the electrons went to the 3d orbital. And let's now draw the energies. We know that our s and p electrons were hybridized in our case. First of all, let's draw 3s electrons. They get all the same energy, 1, 2, and then 3p, 3 and 4. Electrons from 3s and 2 electrons from 2 of 3p orbitals were participated in this process. It means 1s and 2p orbitals hybridized, while 1p and 1d electrons are not hybridized, so I will make them green. These two ones are unhybridized. If they're unhybridized, it means they don't have hybridization, they don't change their energy. They will participate in p bonding, formation of p bond. So we have 3 sigma bonds here. So sp2, these 3 orbitals that hybridized, they participated in the formation of sigma bonds, and 2 unhybridized orbitals participated in the formation of p bonds. As you see, we have 2p and 3 sigma bonds, so everything's okay here. Okay, what if we take ethylene? Let's draw this molecule. And let's find the hybridization of carbon, the carbon atom. Each of them is identical. Let's take the one that is on the left. We see it as 1, 2, and 3, 3 bonding areas. In this case, our carbon atom needs to create bonds with not 4, but only 3 other atoms. So there will be 3 bonding areas, and it means that 3, one will be S, the 2 other ones will be P. We have sp2 hybridization. Well, and now let's draw it. Let's draw the electronic configuration of carbon. We know carbon is the 6th element. If we write the electronic configuration, it will be 1s2, 2s2, 2p2. So we have 4 valence electrons, and let's now draw them in the energetic diagram. 2s2, and above we draw 2p2. This is normal state. What if it's excited, if the atom gets excited? This 1s electron will move to p orbital. So we will get such a form, 1s1, 2p3. This is the excited state and has a higher energy. Overall, we here have what? 4 orbitals. Let's draw them. 1, 2, 3, 4. We said that here we have sp2 hybridization. So 1s, okay, it's 2p, 3p. They got hybridized. The fourth one was not hybridized, so we remove it. The fourth one, as you see, it remains with the same energy. It does not change its energy, so it has a higher energy. It means we have 3 sigma bonds and 1 p bond. So this one is non-hybridized, and it participates in the formation of p bond. It is sp2. And as you see, when carbon creates the bonding with the other carbon, we have the double bond. When we have the double bond, as you know, one of them is sigma, the other one is p. So the p bond is formed by the non-hybridized electron. If we take this book, Organic Chemistry, 3rd edition, David Klein, and find this topic here, we find this picture in that book about ethylene. We see that all 6 atoms of ethylene are in one plane. It's easy to draw. And when we draw it, we can see such a diagram of hybridization of ethylene, of carbon atom in the ethylene. Okay, let's go to other examples. For example, carbonate ion. If we draw the Lewis structure, it will have such a form, and oxygens will have the negative charge, -1, -1. Let's now find the hybridization of carbon. Let's again find how many bonding areas it has. This carbon wants to create bonds with 3 other atoms. If we count like 1, 2, and 3. It has 3 bonding areas or 3 electron areas. So if it's 3, it means 1 will be S and 2 other ones will be P. So we have sp2 hybridization here. To simplify, let's find it. Let's like if we have hybridization and how many bonding areas we have. So on the right side I will write the number of bonding areas, and on the left side I will write the type of hybridization. If there are 2 bondings, 2 sigma bondings or 2 electron areas, it will be S and P, so one of them will always be S, the other one will be P. If it's 3, then it will be sp2, so one is always S. If it's 3, so 2 ones are missing, so 2 ones will be P. If it's 4, that will be sp3. Let's see what happens further. If we have 5, it should be sp4, yes, because 1 S, 4 are missing, is sp4, but we know that P, actually P subshell, has only 3 orbitals. There cannot be 4 p orbitals. Then it means that this is not right. This is wrong. Then we can write maximum sp3. What happened then? sp3, so overall 4, but we have 5. What should we write for the 5th one? 1 plus 3, sp3. So we write sp3, and the one will be D, sp3 D hybridization. If it's 6, it will be sp3d2, sp3d3, etc. Okay. So look, we can draw it like this. We have 1 will always be S. S subshell has only 1 orbital, so one of the hybridized orbitals will always be S. Then maximum 3 ones can be P, so they can be 1p, 2p, or 3p. If it's 2, they will be 1s, 1p. If it's 3, 1s, 2p. If it's 4, 1s, 3p. Then, when all the p orbitals are hybridized, then d orbital can participate, so they can be maximum 5 d orbitals, because we know that d subshell contains 5 d orbitals. So it's always 1s, maximum 3p, and maximum 5 d orbitals. So the maximum hybridization, if we use the maximum numbers from this picture, it will be sp3d5, like that. To make it easy, let's write, if we have 2, 1s, 1p, okay. If we have 3, we have 1s, 2p. If it's 4, 1s, 3p, maximum 3p. Then if it's 5, we have 1s, 3p, and 1d, etc. You can see it in the picture. Well, I think that was clear. If no, you may ask me your questions, you may write in comments, contact me. And now I will draw some molecules here and try to determine hybridization by yourself. You may write your answer in comments and I will answer you. So let's say carbon dioxide, carbon monoxide, and such a big molecule. I will even draw it in the open form to make it easier. So in this molecule you should try to find the hybridization of carbon and nitrogen. In the other 2 molecules you have to find the hybridization of the carbon atom. Try it by yourself, write your answers, and let's check if it's correct or not. That's all. So Hope you liked the video, and I recommend you to subscribe the channel, share it with your friends so that they also can see these videos and learn more. See you in the next videos. Goodbye.